Evaluating the performance of AI models is crucial to ensure they are reliable, accurate, and effective. Here are some key metrics and techniques used in the evaluation process. Key metrics. Accuracy measures the proportion of correct predictions out of all predictions made. It's a basic metric but can be misleading if the data is imbalanced. Precision indicates the proportion of true positive results among all positive predictions. It's crucial when the cost of false positives is high. Recall sensitivity measures the proportion of true positive results among all actual positives. It's important when the cost of false negatives is high. F1 score, the harmonic mean of precision and recall, providing a balance between the two. AUCROC, area under the receiver operating characteristic curve, evaluates the model's ability to distinguish between classes. A higher AUC indicates better performance. Mean squared error, MSE, commonly used for regression tasks, it measures the average squared difference between predicted and actual values. Evaluation techniques. Train-test split, dividing the dataset into training and testing sets to evaluate the model's performance on unseen data. Cross-validation, splitting the data into multiple folds and training/testing the model on different folds to ensure robustness. Benchmarking, comparing the model's performance against standard or state-of-the-art models in the same domain. Bias and fairness evaluation, assessing the model for any biases and ensuring it performs fairly across different groups. Robustness testing, evaluating how the model performs under various conditions and with noisy data. Best practices. Documentation and transparency, keeping detailed records of the model's development and evaluation process. Continuous monitoring, regularly checking the model's performance in production to catch any drifts or issues. Collaboration, working with domain experts to ensure the model meets the specific needs and constraints of the application. By using these metrics and techniques, you can comprehensively evaluate and ensure the reliability and effectiveness of your AI models. If you have any specific models or scenarios in mind, feel free to share, and I can provide more. Absolutely. Overfitting and underfitting are crucial concepts in machine learning that can significantly impact the performance of your models. Here's a detailed explanation. Overfitting. Overfitting occurs when a model learns the training data too well, capturing noise and details that do not generalize to new, unseen data. This results in excellent performance on the training data but poor performance on the test data. Characteristics. High variance. The model's predictions vary greatly with different datasets. Complex models often occurs with models that have too many parameters relative to the number of observations. Symptoms: high accuracy on training data but low accuracy on validation/test data. Example: imagine a model that fits a polynomial curve to a set of data points. If the polynomial degree is too high, the curve will pass through all the points, including noise, leading to overfitting. Solution: simplify the model, reduce the number of features or parameters. Regularization. Techniques like L1 lasso and L2 ridge regularization add a penalty for larger coefficients. Cross-validation. Use techniques like k-fold cross-validation to ensure the model generalizes well. More data. Increasing the size of the training dataset can help the model learn the underlying patterns better. Underfitting. Underfitting occurs when a model is too simple to capture the underlying patterns in the data. This results in poor performance on both the training and test data. Characteristics. High bias. The model makes strong assumptions about the data and fails to capture its complexity. Simple models often occurs with models that are too simplistic relative to the complexity of the data. Symptoms: low accuracy on both training and validation/test data. Example: a linear regression model trying to fit a nonlinear relationship will underfit because it cannot capture the complexity of the data. Solution: increase model complexity, use more complex models, or add more features. Feature engineering. Create new features that better capture the underlying patterns in the data. Reduce regularization. If regularization is too strong, it can lead to underfitting. Visual representation. Here's a simple visual representation to illustrate the concepts. Underfitting. The model is too simple and does not capture the trend. Good fit. The model captures the trend without fitting the noise. Overfitting. The model captures the noise and the trend, leading to poor generalization. Understanding and addressing overfitting and underfitting is essential for building robust and generalizable machine learning models. If you have any specific scenarios or models in mind, feel free to share, and I can provide more tailored advice.